Have you ever wondered how multiplication is performed in digital logic and design? It's a fascinating world that operates on the principles of binary numbers. This is the language of ones and zeros that our digital devices understand and use to perform complex calculations. The magic behind this all lies in the realm of binary multiplication. But what is binary multiplication, you ask? It's a method of multiplying two binary numbers together, similar to how you would multiply decimal numbers. But it's performed bit by bit. Now let's take a moment to visualize this. Imagine two binary numbers. Each one is a series of ones and zeros. The process of binary multiplication involves taking each bit of the first number and multiplying it with each bit of the second number, bit by bit. This multiplication operation is carried out in digital logic and design using a certain type of circuitry known as combinational circuits. These circuits use a combination of logic gates to perform functions like addition, subtraction, and yes, multiplication too. The most popular method of performing binary multiplication is through a binary multiplier circuit. This circuit has the ability to multiply two binary numbers together, bit by bit, just as we discussed earlier. It's a key player in the realm of digital logic and design, enabling our devices to perform complex computations quickly and efficiently. But the world of binary multiplication doesn't end here. There's a whole process and a variety of components that go into making this operation possible. From partial products to the alignment and addition of these products, from carry propagation to the final result, and from AND gates to adders, there's a lot more to explore and understand. Binary multiplication is a fascinating world that underpins the operation of our digital devices. It's the secret language of ones and zeros, working behind the scenes to make our digital experiences possible. So, are you ready to delve deeper into this intriguing world? In the next section, we'll delve deeper into the process of binary multiplication. Binary multiplication might sound complex, but it's pretty straightforward once you understand the process. Let's dive in. The first step in binary multiplication involves creating what we call partial products. For each bit in the multiplier, we multiply it by the corresponding bit in the multiplicand. The result gives us a partial product for each bit position. Now here comes the second step. We need to align and add these partial products. This means we arrange the partial products according to their bit positions and add them together. The third step, carry propagation, is all about dealing with any carry generated during the addition process. This carry is propagated or moved to the next bit position. Once we've gone through these steps, we're ready to obtain the final result. This is done by concatenating or joining together the partial sums. So, in a nutshell, binary multiplication is a four-step dance. Create the partial products, align and add them, propagate the carry, and finally concatenate the results. But of course, this process doesn't happen in a vacuum. There are key components involved in making this process happen. The first of these components are the AND gates. These gates are used to perform the bitwise multiplication of the bits in the multiplicand and the multiplier. The second component is the adders. These are used to sum up the partial products and propagate any carry. Let's consider an example. Suppose we want to multiply 5 by 3 using a 4-bit binary multiplier. The binary multiplier circuit computes the partial products for each bit of the multiplier and adds them to obtain the final result. For an n-bit binary multiplier, this process is repeated for each bit position, and the partial products are aligned and added together. The final result is a 2 n-bit number. There are various design considerations that can be applied to improve the speed and efficiency of binary multiplier circuits. For instance, Wallace tree multipliers and Booth's algorithm are popular optimizations. And for very large multipliers, sequential multipliers can be used to enhance performance. With these steps, you have the basics of binary multiplication. But what components are involved in this process? Let's find out. Binary multiplication involves two primary components, AND gates and adders. Diving right in, let's start with the AND gates. In the world of digital logic, an AND gate is a basic logic gate that implements logical conjunction. It gives us an output of 1 only if both of its inputs are 1. Now, when it comes to binary multiplication, AND gates come into play to carry out the bitwise multiplication of the bits in the multiplicand and the multiplier. That's right, each individual bit of the multiplier is multiplied with each bit of the multiplicand, and this is achieved through a network of AND gates. Now, let's move on to the second core component, the adders. Adders are another fundamental building block in digital circuit design. They are used to sum the partial products that have been generated by the AND gates. But that's not all. They also have the responsibility of propagating any carry that arises during the addition. To give you a clearer picture, imagine a scenario where the summation of 2 bits results in a carry. This carry then needs to be added to the sum of the next pair of bits. Who takes care of this? You guessed it, the adders. They not only manage the addition of bits, but also efficiently handle the carry propagation, ensuring that the final result of the multiplication is accurate. So, in essence, AND gates and adders work together, like a well-oiled machine, executing the binary multiplication process. The AND gates handle the multiplication of bits, generating partial products. These partial products are then neatly lined up, based on their bit positions, and handed over to the adders. The adders then sum up these partial products and manage any carry that arises, ultimately delivering the final result of the multiplication. Now that we understand the components, let's see how this works with a practical example. Consider the multiplication of 5 by 3 using a 4-bit binary multiplier. Remember, in binary, 5 is represented as 101 and 3 is represented as 011. Let's walk through the process step by step. First, we start with the least significant bit of the multiplier, which is 1. Each bit of the multiplicand, 101, is multiplied by this bit. The result is the same as the multiplicand, 101, which becomes our first partial product. Next, we move to the second bit of the multiplier, also a 1. Again, each bit of the multiplicand is multiplied by this bit. The result, 101, is shifted 1 position to the left, reflecting its higher significance. This becomes our second partial product. Note that if the multiplier bit was 0, the partial product would also be 0, regardless of the multiplicand. Now, we add these partial products together. Starting from the right, 1 plus 0 equals 1. Moving to the next position, 0 plus 1 equals 1. And again, 1 plus 0 equals 1. Lastly, our most significant bit is also a 1. This gives us the final product, 1111, which represents the number 15 in decimal. And voila! We've just multiplied 5 by 3 to get 15 using binary numbers and a binary multiplier circuit. It's like magic, isn't it? But really, it's just the power of binary logic at work. Through this example, we can see how the binary multiplier circuit computes the partial products for each bit of the multiplier and adds them to obtain the final result. This fundamental process lies at the heart of digital computation and forms the basis for the complex calculations performed by modern computers every second of every day. While binary multiplication is a fundamental process, there are ways to optimize it. Taking a closer look at binary multiplier circuits, you'll find a world of complex calculations and intricate designs, all aimed at improving the speed and efficiency of this fundamental operation. One such optimization technique is the Wallace tree multiplier. This method reduces the number of partial products that need to be added together by immediately compressing them into a smaller number of intermediate terms. It's like condensing a book into a summary. You still get the main points, but in a more streamlined, efficient manner. Another optimization technique is Booth's algorithm, named after its creator, Andrew D. Booth. This algorithm simplifies the multiplication of 2 binary numbers by reducing the number of additions required. In the world of digital logic, where speed is crucial, this reduction in operations can make a significant difference. Beyond these optimizations, when dealing with very large multipliers, sequential multipliers come into play. These are multipliers that incorporate a pipeline, a series of data processing stages where the output of one stage is the input of the next. This allows the process to be broken down into smaller, manageable tasks that can be performed simultaneously, improving overall performance. But why does all this matter? Think of binary multiplication circuits as the heart of digital systems. They're essential in arithmetic logic units, or ALUs, within processors. These ALUs are where the magic happens. They perform the arithmetic and logical operations that drive our digital world. So, understanding the principles and components involved in binary multiplication isn't just an academic exercise. It's a journey into the core of digital logic design, a peek into the engine room of the digital universe. Whether you're designing the next groundbreaking processor, or simply trying to understand the digital world a little better, I hope this exploration of binary multiplication has been enlightening Understanding the principles and components involved in binary multiplication is essential for digital logic designers. We hope this video has shed light on this fascinating process.